So here we want to approximate the integral from 0 to 3, integral from 0 to 2 of 4 plus xy squared minus 2x dy dx. For emphasis, y is the inner differential, so this is y. So y ranges from 0 to 2. X is the outer differential, so x ranges from 0 to 3. So I would like to subdivide that into a certain number of intervals. So let's see, y goes from 0 to 2, and x goes from 0 to 3. So we have 0, 1, 2, 3, 0, 1, 2. But let's go ahead and separate all of these as well. To just increase the number of rectangles that we have. So moving across, we have, it looks like a total of 24 rectangles. Let me label them. And I'm going to need to find the midpoints. So let me label the midpoints here. Halfway between 0 and a half would be a quarter. Halfway between a half and 1 would be 3/4. Halfway between 1 and 1.5 would be 1 1/4. Halfway between 1.5 and 2 would be 1 3/4. Halfway between 2.5 is 2 1/4. Halfway between 2.5 and 3 is 2 3/4. Over here, halfway between 0 and a half is a quarter. Halfway between a half and 1 is 3/4. Between 1 and 1.5, 1 1/4. Between 1.5 and 2, 1 3/4. So we've got all of these midpoints. Let's label those 24 rectangles and use our spreadsheet to approximate this double integral. Notice for the first 6 rectangles, the y value is all 0.25, and then the x values change as we see there. Let's go ahead and identify that. All the y values are 0.25, and then you see the x values stepping up a half each time. Now, for the next 6, the x values will be the same, but the y values now jump up to 0.75. And that's going to be our pattern. And then for the 6 after that, the x values are going to be the same. That didn't work. So the x values being 0.25, 75, 1.25, 1, 2, 3, 4, 5, 6. Put them here. And then the y values this time jump to 1.25. Let's autofill those. And then for our last 6, again, the x values are the same, and the y values jump to 1.75. So, I mean, this is a tedious process, but it's a nice way to kind of visualize what's happening. We're building Lego towers on each of those 24 blocks. Now what I have to do is I have to figure out my height is. So it's 4 plus x times y squared minus 2x. So equals 4 plus the x value times the y value squared minus 2 times the x value. Now this actually could go below the xy plane. You could have some negative z values. That's possible. Let's autofill this. So indeed, we had a couple spots where we have negative z values for those rectangles. So let's kind of visualize what we're dealing with here before we continue. So I want to go ahead and look at the graph one more time. So there's our surface. We see our surface. And this is our typical perspective that we prefer. And then what is our region of integration? There it is, as best we can tell. 0 to 2 in the y direction, 0 to 3 in the x direction. We have some shadowing here that's a little strange. But this is what we're dealing with. This is what we have. We want to find that volume. So indeed, we see some that are dipping below the z-axis. So let's jump back to the spreadsheet. I need to determine what the area is of each rectangle. Now, the area here is what? Let's go back and look at our rectangles. From 0 to 0.5. We split from 0 to 1, so this is 0.5 here, and this is 0.5 here. So each rectangle is 0.5 wide and 0.5 high. So the area of each rectangle is 0.25. Let's go ahead and put that back in the spreadsheet. All of the areas are 0.25. And then the volume is the height times the area. And then we're going to want to sum that up to get our approximation for our double integral. Volume is height times area. Height times area. We get this. And then we want to total all those up to get our volume. Volume equals the sum for our approximate volume under that surface over that region, keeping in mind if it's below the axis, that's perceived as negative. And we get an answer of 17.8125. So that's our best guess for that integral. If we wanted a better approximation, we would use more rectangles with smaller areas, and that should get a little closer to what the answer actually is. But let's go ahead and do it out longhand to see just how good our approximation is. So this is what we start with. Y is the inner differential, so Y is here. X is the outer differential, so X is here. And we begin with the inner integral. What is the inner integral? Integral as Y goes from 0 to 2 of 4 plus xy squared minus 2x. Y is perceived as a variable. X is perceived as a constant. So that is our inner integral. What do we get? We get 4y plus xy cubed over 3 minus 2x is perceived as a constant times y, evaluated as y goes from 0 to 2. So what is my inner integral going to be? 4 times 2 plus x times 2 cubed over 3 minus 2x times 2 minus a whole bunch of zeros, 0 plus 0 minus 0, as is often the case. What does my inner integral become? 8 plus 2, 4, 8/3 of x minus 2x times 2 minus 4x minus 0. Where does that get me for my inner? You get 8. That's 8/3 minus 12/3, 8 minus 4/3 of x. So that all gets substituted for the inner integral. And then to finish this, I just take the integral as x goes from 0 to 3. So my outer integral, x goes from 0 to 3 of that inner integral. 8 minus 4/3 x dx. So let's see what that gives us. We get 8x minus 4/3 x squared over 2 evaluated as x goes from 0 to 3, which is 8x minus 2/3 of x squared as x goes from 0 to 3, which is 8 times 3 minus 2/3 times 3 squared minus 0 minus 0. What does that give me? 24 minus 2/3 of 9 minus 0. 24 minus 2/3 of 9 is 6. The integral is 18. So my conclusion then is that the integral 0 to 3, 0 to 2 of 4 plus xy squared minus 2x dy dx actually equals 18, So my approximate answer, if you recall earlier, our approximation was 17.8125, which is a pretty good approximation with only 24 rectangles for this thing that is quadratic in nature. And again, let's remind ourselves what this really means. The volume above the region is perceived as positive. The volume below the region is perceived as negative. Positive minus the area below gives us our answer of 18.